In this video, I'm going to work you through how a healthy brain would overcome the tendency to read green here when you're supposed to say the ink color red, as we've seen in the Stroop task. And the reason why I'm going to work through this example is to give you an idea how people then think of sort of models of the brain and generate predictions based on these models, and then actually go on and actually test those models and see if there's any evidence for the way in which the brain is actually working. So if you want to model conflict processing, this is useful, right? Oftentimes cognitive psychologists and theories build models, and then the point is to generate new testable predictions so that you can actually test the models. And then in this particular example, we're going to see an example of modeling the Stroop task and see if we can learn anything about how the brain actually works. Now, we've already seen similar examples of this, so this really meant as an example of how modeling can be useful. It can be done for other tasks as well. We already saw it for example, processing of words and letters with the feature level, the letter level, the word level, and then from the word level there were connections back to the letter level and so forth. It's one example of a neural network model where basically these are different levels, different layers where different neurons are firing, and then they connect to each other and it creates this whole neural network. And models that use this neural networking are actually very successful in capturing aspects of the brain and of behavior. So let's do this for the Stroop task and get ready for a whole bunch of boxes and arrows. So, and this is ironically called the simple version, okay? So here's what's happening. Let's keep this simple, and let's say that we're dealing with four possibilities. People either see the word green or the word blue, and that word is either printed in green or that word is printed in blue. So in that case, let's just say that we have four neurons. Two of the neurons respond to color, one of them to green, one of them to blue. And then there's two word neurons, one word node that responds to green and one that responds to blue. So these color neurons would be in the occipital cortex, right? That's where vision happens. And you see actually that there's lateral inhibition going on there too. Remember, when neurons push each other down, they want to fire and they push their neighbors down. So if something green shows up, the color node green starts to fire and it pushes down the color node blue. And it also connects to the response green, whereas the color node for blue would correspond to the response blue. That's the color nodes. We also have the word nodes, which we find in the temporal cortex, because that's where language is being processed. And there we have, let's say, one neuron or one word node that corresponds to green. Whenever it sees the word green, it starts firing and tells the response layer, hey, you should say green, 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 green. And again, there's lateral inhibition to the word node for blue. If blue sees itself, the word blue is spelled, blue starts firing and starts screaming at the response layer to say blue, 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 blue. And you see there's even at the level above here about the response layer gets input from the color nodes and from the word nodes. The more input it gets for green, the louder green starts screaming and you want to say green. And then there's also lateral inhibition so that the more green fires, the less blue is going to fire. Okay? Now, here's the thing in this model. You see this, that the thickness of the lines from the word nodes to the responses is thicker than the thickness of the color nodes to the response layer. And the reason for that is that we've seen that people are way more automatic at just reading out the words than they are at naming the color. So a priori, people are inclined to just read the word, and that's going to feed into the response layer more strongly than saying the color of the ink. So now that that's the case, we have an issue then, because if that's true, then how are people ever going to ignore reading the word and actually focus on the color instead? So we need a couple of additional layers here to actually account for how behavior actually arises and how people are able to do this task correctly. So what's interesting here, right, it's a couple of things. There's competition at each level of the model. You see that there's that lateral inhibition going on, just like we saw in perception for MAC bands and for word processing with these top-down influences. Competition is captured in the inhibitory connections between items, which is lateral inhibition. But the question really is, how do people overcome the stronger influence of word nodes over color nodes, so that we're not always just reading the word, but we are actually able to slow ourselves down, inhibit reading the word, and then actually say the color of the ink? Well, for this, we're going to include executive attention in the model. And it's going to do that in two different ways, because there's really two different mechanisms here that can be helpful. First of all, we need to have something that sets us up beforehand. Basically, the second you're being told, hey, you're going to say the color of the ink, rather than reading the word. Our system, in some ways, as soon as you're being given this instruction, you know, oh crap, this is going to be the difficult condition, because I'm going to be inclined to just read the word. I'm going to need to stop myself so that I'm not actually doing that and start naming the color instead. That's before the task even happens. Now there's a second part where when the actual word shows up, it may be that it's green printed in green and everything is great, or it may be that the word reads green but it's printed in blue, so that actually there is a conflict and we now need to resolve it. The model deals with that in two different ways. First of all, there's this attention controller, which is located in the dorsolateral prefrontal cortex. And the attention controller deals with the thing that I just described before the task happens. It detects whether the task is going to be to name the colors, and if it realizes that colors are needing to be named, it's actually screaming at the color nodes and telling them, hey, you need to pay more attention, so that their connection to the response layer becomes thicker than the connection from the words to the response layer. So you see here the attention controller can actually ramp up input from the color node so that the correct response is being given based on the color rather than the word. That's step one, and that's supposedly in the dorsolateral prefrontal cortex. Step two is this conflict monitor, which really starts operating once an actual word shows up, and it detects whether the word, what it spells, is the same or different from the color of the ink. So how do we come to a model like this, right? Why these particular brain areas? Well, this is based on a large literature, and you don't really need to worry about the details of this, but there's lots of evidence that the dorsolateral prefrontal cortex and the anterior cingulate are two systems that get activated when there's actual conflict going on in the Stroop task. So the idea here is that the dorsolateral prefrontal cortex manages the executive attention part, and the anterior cingulate manages the actual monitoring of conflict when it shows up. Now, talk is cheap, but can we actually make some new predictions then? Well, it turns out a paper in 2002 did exactly that. So the idea is that people are being shown beforehand if the task was going to be to read the word, which would be easy and require no additional attention, or to name the ink, which would require that the color nodes get more strength, more input than the word nodes do. So people basically knew beforehand if they needed executive attention or not. And then the question is, does the dorsolateral prefrontal cortex become active before the task is presented, just because, quote unquote, it knows that conflict may arise? That's question one. And then question two is whether, when there is actual conflict, right, blue printed in green, does the anterior cingulate then become activated, and not the dorsolateral prefrontal cortex necessarily anymore? So this is what they did. They put people in the scanner, had them do the Stroop task by either reading words or naming colors, and then the question was whether the activation of these two different areas would actually change in the way that they predicted. So here's the graph, and you see here the top two plots from the anterior cingulate, so supposedly the conflict monitor, and the dorsolateral prefrontal cortex on the bottom here, which is the attention controller. And what's happening here from left to right is time is progressing. So this is the very start, where people are being told in this first phase whether they were going to need to read the word or name the color. And you see there that during the time when they're instructed, you see indeed that the dorsolateral prefrontal cortex becomes more activated when people are being told to name the color versus read the word. And that is exactly in line with the prediction. you see in that same period before the actual conflict shows up that the anterior cingulate shows the exact same level of activation for the two tasks. Now right here, the actual word shows up, so that people are now either looking at a conflict case or they're looking at a case where the letters actually spell the color of the ink, in which case there's no conflict. And once that happens, you see that at that point, the anterior cingulate actually ramps up its activation for incompatible trials compared to compatible trials. So meaning you see the word green spelled out, but the ink color is red. So you need to say red. In that case, the anterior cingulate is more activated than when you're reading the word red that is also printed in red. Those would be the compatible trials. Meanwhile, activation in the dorsolateral prefrontal cortex at that point, once you're actually looking at the word, is no different. Sorry about that. So what's happening here is that the data here confirm both of the predictions. Indeed, the dorsolateral prefrontal cortex is involved with directing attention before the task actually shows up, whereas the anterior cingulate is dealing with conflict on the go as you're really looking at it. And to pull this out of this boring kind of task and apply it to more real life examples, right? Let's think about when we need to direct our attention and kind of be more aware. Well, one situation, for example, where that might be the case could be in a job interview. So in a job interview, you know beforehand that you need to be kind of focused, really make sure that you're not going to drop any inappropriate words, right? No cursing involved, none of that. And all of that sort of ability will be handled by your dorsolateral prefrontal cortex. So that when you walk into the interview room, the dorsolateral prefrontal cortex is actually engaged and will help you with inhibiting any inappropriate response. Then you're in the interview, and let's say you're being asked some difficult question. Well, at that point, the anterior cingulate will actually kick in and start sort of ramping up your processing and your need to resolve the conflict right on the spot. Okay? And you can think of this in the same way when, let's say you're in a bar at night and somebody's starting a fight with you. In that case, the anterior cingulate would start ramping up so that you're dealing with literally conflict right on the go. So both of those brain areas are extremely important, and they're very useful in either sort of almost planning for conflict, which is the dorsolateral prefrontal cortex, and then dealing with conflict as it actually arises, which is handled by the anterior cingulate. Now, what's interesting too about the prefrontal cortex is that it's actually involved in reasoning as well, and reasoning also is an expression of executive control. So how do we know this? Well, they've done studies with Alzheimer patients and control patients where they gave them two objects and they had to pick one of the two objects to fit a particular description. And they did this in two different conditions. First, in a similarity condition where they would just ask people, hey, are these two objects similar or not? And, if you're being given a quarter and a pizza, you could say, well, yes, they're similar. They're both round, or no, they're not similar. One is food and one is not. One is money. There's not really a correct answer in that case, but that's not the important condition. The reasoning condition is the important condition, where you ask people which one of the two is an object that is 3 inches in diameter. So you have to pick between either a quarter coin or a pizza. Now, neither of these two are typically 3 inches in diameter, right? A pizza is typically larger and a quarter is necessarily smaller. So once you reason through this, it has to be that the correct answer is a pizza, because a quarter, if it changes size, it's not a valid coin anymore. Whereas a pizza, albeit not a regular size for a pizza, you could conceivably make a pizza that is 3 inches in diameter. So the correct answer would be a pizza. And Alzheimer patients consistently would fail in that kind of condition because, again, reasoning would also involve the prefrontal cortex. And in the case of Alzheimer's, we know that people actually have damage to that area and they have trouble completing that condition successfully.